And the other part of section 2.4, I don't know why they put it all in the same section. It seems like it should be a whole other section to me, but we'll go with it. So I'm going to talk about points of concurrency and concurrent lines. So first of all, we're going to talk about perpendicular bisectors. So if we have a segment right here, a perpendicular bisector is going to form a right angle and it's going to cut it in half. Okay, so it bisects it and it's perpendicular. Okay, and then you have to remember that then this goes on forever and ever up there. Alright, now a triangle could have 3 perpendicular bisectors in one triangle. And I'm just going to go ahead and move down here to the set of diagrams. So if I use each of these triangles, okay, and I do the perpendicular bisectors of each side. And I'm going to just eyeball it, okay? Bisect, go perpendicular. Bisect, go perpendicular. Bisect, go perpendicular. Now what will happen is they will always be what we call concurrent. So the point right here would be the point of concurrency. Okay? And for the point of concurrency of perpendicular bisectors, that's going to be called the circumcenter. Now that was an acute triangle. What happens if we do the same thing with a right triangle? I'm really bad at this one. I'm just guessing on the pieces. Okay, so I've got my perpendicular bisector. That's not very good. Perpendicular bisector. And then the perpendicular bisector on that one. And what happens on that one, it's actually the point of concurrency is actually on the hypotenuse of the triangle. It's on that long side of the right triangle. And when we do the same thing with an obtuse triangle, for bisector, go perpendicular to that. Bisector, go perpendicular to that. Bisector, go perpendicular, and that point of concurrency is actually outside the triangle. Okay, so the point of concurrency of the circumcenter is outside the triangle. So it can be inside the triangle, it can be on the triangle, it can be outside the triangle. Okay, so what good does this do us? Alright, the circumcenter, okay, so a couple things. Any point on the perpendicular bisector is equidistant from the endpoints. Okay, so if I come back to that top diagram, oops, too far. If I just pick any random point on that perpendicular bisector, it's the same distance from this endpoint as it is from this endpoint. Doesn't matter where I pick it. I could pick it anywhere. I could pick it here. This segment is going to be the same distance as this segment. So that's the special property of a perpendicular bisector of a segment. Now, the perpendicular bisectors intersect at the circumcenter. The circumcenter is equidistant, same distant from each vertex of the triangle. So that's the special property for the triangles. So let's do some examples with those things. So if you have a perpendicular bisector, so look for the markings. Perpendicular, these tell me that it's a bisector. So that dashed line is a perpendicular bisector. It's not erasing for me. There we go. So the dashed line is perpendicular bisector. All that means is if this is 8.5, then this is 8.5. Okay? Now, this one, the thought's the other way around. Because it's a bisector, and it's equidistant from the endpoints, then it must also be perpendicular bisector. So if that piece is 6, xy is also 6. Same thing here. We see perpendicular, we see bisector. These two things have to be the same. And I can solve for x, and x equals 2. I can plug that back in. 3 times 2 is 6, plus 1 is 7. And the two sides would each be 7. Okay, so circumcenters, perpendicular bisectors. So, I'm just going to go circumcenters equidistant. So the property here is that, property is that it's equidistant from the vertices. So I'm going to use green. The distance from the vertex to the circumcenter, that's the same as that, is the same as that. So, if you needed to find, 3 friends lived in 3 different cities in the United States, and you wanted to meet at the point that is the same distance for everybody, you could, theoretically, you could get out a map, draw that triangle, construct your perpendicular bisectors, and that'd be the spot. It's the same distance from everybody. And while it may seem kind of weird, on this one, it's these that are all the same. Okay? It's this segment is the same length as this segment is the same length as this segment. So it's just that gives you the one spot that's the same distance from all the vertices. Alright, so then we have another bisector. And instead of bisecting a segment, we could bisect an angle. So if we have an angle bisector, it's the ray that cuts the angle in half. Okay, we've used those. I'm really not very good at guessing an angle bisector without measuring. Okay, so we could cut an angle in half. Okay, then any point on that angle bisector is equidistant from the sides. Now, distance from a point to a line, we have to make sure we're measuring perpendicular. So, if this is perpendicular, these two things would be the same, no matter where we pick that point. Okay? We could pick it down here. That perpendicular little segment would be the same length as that perpendicular segment there. Okay? And again, I could do all 3 of them in any given triangle. And they are going to be concurrent again. So if I do the angle bisector, again, I'm not always very good at judging these. Bisect the angle. Bisect the angle. And it's not very straight. Bisect the angle. They will always be concurrent. So we have a point of concurrency again. Okay, I could do it with the right triangle. So I bisect the angle. This one I gotta get rid of 45. Bisect the angle. Bisect the angle. Bisect the angle. And if we did it exact, they would definitely all be concurrent. Okay. Do it in the obtuse triangle. Yuck. So, that one's really not very good. Notice where these are. If I bisect, 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 every single one of them is inside the triangle. And look at the name of this thing. It is the incenter. Okay? The incenter is always inside the triangle. So if we do the angle bisectors, we get an incenter. Now it has a special property. It is equidistant from the sides of the triangle. I'm going to do it in green. So if I drop down this perpendicular, if I do this perpendicular, and if this was constructed all nicely, those 3 green segments are all the same length. Okay, it's the same distance. Distance from a point to a line has to be perpendicular. That guy, if that's perpendicular, and if that's perpendicular, those are the ones that are the same length, equidistant from the sides. And it's a little harder to draw on this one. Those three green ones are all the same length. Okay, so we can find that points of concurrency. So if all you just have is an angle bisector, oops, oh, I don't even have no examples on here. So any point on the angle on the bisector is equidistant from the sides. They intersect at the incenter, which is equidistant from the sides of the triangle. Alright. That is bisectors. I'm going to do the others in one more video.